All right, hello everyone. This video is supposed to take place of the office hour recording I was asked to do. However, we didn't really have many insightful questions outside of the problem set, so I couldn't really record many explanations because there were no explanations. So let's just go ahead and walk through the stuff that I had planned to walk through on, and maybe go over some of the practice problem sets I had posted in the chat. All right. So let's go ahead and share my screen. But the first thing I want to bring attention to is reactions of chapter 6 that's posted on campus. Now you can access this file by going to the files tab, going to test 2 study material, and this should just scroll down and this should be there. All right, now this is a really nice comprehensive list, and it has pretty much most of the alkene reactions you need. I say most because there are like some variations that you kind of have to understand the content on, which is kind of the point of class, is understanding the content. So I'm gonna leave that kind of studying for you guys and for you guys to ask during office hours, or ask Dr. Berg during his office hours, or during class. And in regards to these reactions for flashcards, that's probably the biggest tip I have, is putting in the time and effort into learning these reactions, because this is organic chemistry and you need it. If you're going pre-med, pre-vet, take the MCAT, take whatever test you need in order to get into graduate school. You need to understand this. And if you find, I don't think there's a way to BS this, but even if there was, you can't really BS your way through this. You have to just straight up memorize all of this. I see all of this by this information, but you just have to memorize these patterns and these reactions because they're important and they're useful. And that's kind of, yeah, just the point. So with that little note being said, let's go ahead and move on. So this was, all of these reactions listed here are reactions that you need to memorize, like I just said. It kind of does look like a lot, but if you put in the time and effort to make flashcards, does not look like a bunch. And once he released the practice or the problem set answers, making flashcards with those is what I did, and extremely helpful. And during class, he went through a bunch of mechanisms, right? Going through like where electrons are, where the electrons in like a double bond, which atom it attacks. Now that's important to look over. However, even though he did that for every one of the reactants we had, the main 3 you need to memorize step by step are these 3, just the first 3, because these are super interesting. And if you know how these mechanisms work, you can kind of figure out how the other mechanisms kind of work. So these are kind of like our primary colors of that color wheel. If you remember art class, these are our primary colors. And if you mix and match and you know it, you figure out the rest of these. But knowing these and their mechanisms is pretty much essential, because they're task questions. It's going to be one of these 3. And good news, yeah, it's just these 3. For the rest of them, you kind of just have to memorize the reactants, the reagents, and predict the product. So like some questions he might give you, all right, if you have this reactant and this product, he might ask you, he won't give you this, what are the reagents? Conversely, he might give you a reactant and the reagents, and he might be asking, what's the product? Those are the types of questions he'll be asking. And that's why it's super important to make flashcards so you can memorize this stuff. So take a look at this, take a look at that thing I posted in the group me. Again, put in that effort, and you guys, I know you guys are smart and you guys will figure this out. And hopefully this will be pretty helpful. And if you follow my advice and take the time to practice, you would have taken a crack at the problem sets that I posted. And right now, I'm just going to go over the problem sets, group 5, both of them. So let's go ahead and go through problem set 4. All right, and just work our way through it. Okay. Oh, there we go. So the rule for naming alkenes is an alkene is a priority group. It takes priority over branch status groups. So that includes the halogens, ethers, other alkyl groups. It's a priority group like alcohol and amines, but not quite as high on the list as those groups. Like if you remember from class, if you have an alcohol and an alkene, an enol, the alcohol would take priority. But somewhere in the middle is that status for the alkene. So that in mind, let's go ahead and try naming this. So if this is our compound, remember the first step is identifying the parent chain. And from the looks of it, this right here is our parent chain. It's going to be a hexane, but it's a hexene because of our alkene, but we'll get to that later. I'm looking at the ends of the parent chain, and there's no methyl or ethyl group that I can send it with. So I do know that the parent is a hexane. We'll change it soon. We have an alkene here, so we know it's going to be a hexene. And let's go ahead and number it both ways. 1, 2, 3, 4, 5, 6. The other way around. 1, 2, 3, 4, 5, 6. All right. Well, if our alkene takes priority over these methyl groups, then our gray pattern would be correct. We want alkene to be 2 compared to 4. 2 compared to 4. And when you number it, the number you denominate out, the alkene is always going to be the first carbon you come across before crossing that alkene bond or that double bond. So this would be a hex 2-ene. And if that's our parent chain with the respective suffix, then let's go ahead and add our prefixes. And we have 3 methyl groups, so it's going to be a trimethyl. And if we're using our gray numbering, we have 2, 3, and 5. So we have a 2, 3, 5 trimethyl hex 2-ene. All right. Now, he throws us a cyclic compound. Now, for the cyclic compound, this is pretty interesting because, like, if you remember cyclic compounds with alcohols or amines, the first carbon is always the carbon with that alcohol or that amine or that priority group in general is. Now, that's still true for priority groups, and alkene is a priority group. So there's no alcohol or amine present. So the highest priority group is that alkene, and our first carbon has to be one of these alkene carbons. So if this is 1 or this is 1, well, let's try our numbering both ways around. Let me erase this real quick. Oops. So if we did the purple side, let's just start here. All right. Now, if we start at this carbon, we cannot count this way. If you count the alkene, whoops, sorry, I'm not used to drawing on Word. You have to cross the alkene in order to number it. So if you started here, you'd go 1, 2, 3, 4, 5, 6. So if you had the 1 to 2, our alkene or cyclohexane, that's our parent. Our denominations where that numbering would be 4 and 6. However, if we went the other way, what if we started with this one? 1, 2, 3, 4, 5, 6. Our number system would be 3 and 5. The 3 and the 5 would be preferable. So that's how our denomination works. We have a chloro, 3 chloro, and a 5 methyl. So it's going to be 3 chloro, 5 methyl, cyclo, don't forget your cyclo, hex 1-ene. And kind of like the alcohol, if you just write, these 3 dots denominate what I just wrote there, hexene. Without the 1, it's still acceptable, but it's a pretty bad habit to exclude the 1, because if it was a 2 or a 3, you would have to include that. All right. All right, let's get into this one. Okay, so if we have a parent chain, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. It's the same both ways. So whichever way we go, I'm just gonna go, oh, come on. Whatever, I'm gonna go this top route. 1, 2, 3, 4, 5, 6 with a propyl group. Or I can go the other way. 1, 2, 3, 4, 5, 6. Now, the green way, we have our alkene denominated as 2, but this magenta way, we have our alkene denominated as 4. And the alkene being a priority group, we want it to be 2. So our parent chain is going to be a hex 2ene. And then don't forget our prefix, our 3-propyl. So we would have 3-propyl. We don't have any other branches, thankfully. 3-propyl, hex 2ene. Now we get into an enol. Now, enols are weird because you can fit in 2 suffixes, and that's something we haven't seen. Now, let's just first off identify our parent chain. We have our parent chain of, oh, come on, 1, 2, 3, 4, 5, 6 is a hexene, but it's a hexene because we have an alkene right here. Let's number it. 1, 2, 3, 4, 5, 6. The other way around. 1, 2, 3, 4, 5, 6. We have a priority group OH, whichever one is short or the smaller number we have to go with, which is the 3. And thankfully that works out too, because our alkene is also denominated as 2, which is preferable. So if we were to name it, we would have hex 2ene. However, we also have 3-ol. Hex 2ene 3-ol, an enol. And don't forget, you have to drop that E if it's only one alcohol. If it was a diol, you would keep that E. Let's erase this, because as it is right now, the answer we put down is incorrect, or it's still mostly incorrect. Oh, please, for the love of God. There we go. Okay. Let's clear this up. And I'll just give you a hint. I won't give you the answer of what we have wrong, but this is something that you always have to pay attention for. Whenever you have an alkene, right, with an alkene, oh, come on, I did not fix an alkene with different groups, like this has a methyl group, this has an H, this has a propyl group, this has an OH. There's a kind of denomination you have to put there. So it's missing a certain suffix. I'm just going to leave it there, and hopefully you guys can figure it out. You have to look back at your notes. Now, when you do figure it out, you might be thinking, why didn't we do that for this compound right here? Well, it's not really applicable because both of these are propyl groups. And if it's the same way both ways, there's no denomination that can distinguish the two. So you don't need it. Now, let's go into a diene right here. Now this parent chain is going to be cyclo 1, 2, 3, 4, 5, 6, 7 cycloheptene. This is cycloheptane, but you have 2 alkenes to be cyclohep. Whoops. Come on. Heptadiene. Now we just have to number it. Again, we need to number it in a way that minimizes the numbers for the alkenes. So if we renumber it, we have to, if it's a cyclic compound, we have to start an alkene, barring there's no alcohol means 1, 2, 3, 4, 5, 6, 7. We go around 1, 2, 3, 4, 5, 6, 7. We have a 1 versus a 4 and a Come on. 1 versus a 5. 1 versus a 4, 1 versus a 5. The 1, 4 is what we want. So we would get a cyclohepta 1, 4 diene. All right. Now, let me move on to this. Now, some of you summer session folk might have a compound like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You might have something like this. All right, where your only branch is an alkene group. Now, what you're used to is looking at the longest parent chain, which is correct, what you normally do, longest parent chain, and then naming any kind of branches that stick off from it. And if that was the case, you would have an undecane. However, you don't know how to name that branch alkene. Well, the thing is, for the priority group, you need to include this in the parent chain. So instead, it would be a 1, 2, 3, 4, 5, 6, 7, 8 in octane with a 1, 2, 3, 4 butyl group. And the octane, you just treat it as if it was an alkene. So if you treat it as an alkene, alkene, it would be oct1ene. If we were to number it, that way, 1, 2, 2 butyl octene. Nope, no dash. Butyl oct1ene. All right. And that kind of goes for something like this as well. If you were to have a compound like this, all right, if you were to treat this 2, 3, 4, 5, 6, 7 as a heptane, how would you denominate this branch if there's a methyl there? Well, you don't. OH is a priority group, and you need to include that in your parent chain. So your actual parent chain would be this right here, 1, 2, 3, 4. So it would be 2, 3, 4, a butyl, butan, 1, all, 1, 2, 3, 4. Hopefully you guys start seeing that pattern. All right. Let's move on to this one. All right. Problem set 5, group 5. Again, this should be similar to what you guys have on your problem set, but not exactly. So it can be helped. So you see here, this right here, just as a whole, if you're in the fall or spring, you will just be straight up have this as a page on the test, and you just have to predict the products. And in this case, we're doing exactly that. If we go back to what I talked about earlier, that's what we have right here. We have a reactant, we get reagents, and we have to predict the product. So let's go ahead and do that here. So HI, that's hydrohalogenation, right? So we have a secondary and tertiary carbon. Where would the carbocation want to go? It would want to go here. That's where the iodine would attack. So it would be HCC3, CH3, CH3. It would attack. Our HI would go into like this. Oh, come on. All right, the correct title, again, give me 1 sec. Recording. Okay, now we're going back to this here and excuse me here. All right, now let's just get down the line. So again, we have a tertiary, and a secondary. That's not how I want to draw it. Now I'll just keep it as it is. Now, this is a hydration reaction, kind of like the one we just did. This is one of the mechanisms you have to memorize. And in this situation, it would add an H and an OH. It splits up that water, hydration. And the OH would add to the most substituted. So it would be OH, CH, H, CH3, where that former alkene was right here. I'm just going to keep them in magenta so you guys can keep track of what's adding. Go here, we have a halogenation. However, we have a aprotic group, so it would add 2 BRs. And if you remember that this is anti-addition, so stereochemistry does matter. We break up that alkene, we get CH3, anti-addition, let's do BR, BR. And if it was anti-addition, oh, come on. Anti-addition. Another thing we can accept, if you pancake flip it, we would be able to accept this. And it's the same thing. For solvation, now this is the third one they have to memorize. We have to add across that alkene right here. And you would get CH3, H. This is primary, this is secondary. The most substituted one gets our main group. Our least substituted one gets our, this is supposed to be 3, gets our hydrogen. And we have another hydration. Right? Now note, this is a secondary. This is also secondary. This forms a carbon-cation intermediate. Where that H would be added. Now, normally you would add an OH here. However, we have a methyl group that could shift over, and this is one of the ones you have to know shift happens. And that OH can basically add elsewhere. Basically, it can move that carbocation. So if this methyl were to shift over, come on. That carbocation would be on a newly tertiary carbon compared to a secondary. And that's where our OH can add. So let's go ahead and draw it like this. There we go. Again, we have a bromination. However, for the bromination, this is an aprotic, so we'd add 2 BRs that are anti to each other. The thing to note, though, is that bromination, or just halogenation, there's an intermediate where BR is like this. There's no carbocation intermediate, or at least not that we see. So there would not be any shift. Again, that's the intermediate. And this is anti-addition, don't forget. So in real life, they would be anti to each other. MCPVA, that's one of our big peroxides that basically eliminate that alkene and just puts an oxygen between the two. So you can literally just write what you see. Now, this might look correct, but you have to include stereochemistry or do some kind, because this epoxide is on one plane. So the most correct answer would denominate all of these in a more 3D connotation. Another way we could accept it is if you just left it as this, if you just wrote like this is all cis to each other, we would accept that, just so you know, like they're on the same side. Now this one is a little harder. We have a partially negative, partially positive end, because remember, bromine is higher up in the periodic table, is a lot more electronegative than iodine. We have one that's an electrophile, one that's a nucleophile. And the nucleophile, the negative charge, attaches where that positive carbocation is. That's the key. And if we were to break this up as it was normally, right, we can treat it as like BRH, kind of. HBr, partially positive, partially negative, same deal. This alkene would attack that partially positive atom, and in this case, it would be iodine. So we'd have C, C, H, H, I, positive charge, CH3, CH3. It adds in a way so that the positive charge is on that tertiary carbon right here. And then we would have our positive, not positive, our partially negative atom, Br, attacked this. So our final product would be 3 C, C, H, H, CH3, BRI, the most partially negative one being on the most substituted carbon. Now, this last portion, we have two products, and that makes sense because we have a relatively symmetrical alkene. We have, if we were to expand this, we don't know if it's cis or trans because of the way it's written. However, we do know that either way, we have a secondary. If they're the same, if the alkene is on the same kind of substituted carbon, then there's two possible products. Those possible products basically add, right, scenario 1, H adds here, Cl adds here. Scenario 2, Cl adds here, H adds here. And just draw those out. So it would be CH3, CH, CH, CH2, CH3. These two being where the original alkene was. Let's do HCl and then again, this is being our original alkene. ClH. There you go. This goes over problem set 5 for a different group. Hopefully gives you some insight on what you kind of want to do for the next problem set, right? So I'm going to stop my share here. I think that does it for today. If you guys have any questions, email me, come to office hours. It's really helpful if you just ask questions to me or Dr. Berg. Other than that, happy memorizing.